This is an example where we're going to apply the mechanical energy equation, also known as the extended Bernoulli equation. So in this example, water is to be pumped from a large tank with an exit velocity of 6 meters per second. The original 1 kilowatt power pump does not supply the necessary velocity. The question is, how much power W dot must a second inline pump supply? Now we're also given an expression for the head loss in the system. So H sub L is our head loss, and this is a function of the flow rate Q, where H sub L is in meters, so units of meters, when Q, our flow rate, is in meters cubed per second. So let's draw our system down here. We have a large reservoir, which is filled with water. And there's some pump up here. This is our first pump, number 1. And there's some piping system that connects these two. And we have an outflow from this pump. And we are going to need a second pump. This is pump number 2, leading to our outflow. And the outflow velocity we know must be 6 meters per second. And we're also told that the nozzle area is A equals to 0.01 square meters. And finally, we're also told that this vertical distance is 2 meters between the surface of the reservoir and the outflow of the pump. So we are going to define a control volume here, and our control volume is going to be essentially right from the surface where we're going to be drawing this from, and it's going to extend up and basically cover our entire flow system. So we're drawing from the reservoir surface where the velocity is 0, and the water will be expelled from the end of this nozzle where the velocity will be 6 meters per second. And so to that control volume, we are going to apply our extended Bernoulli equation. So we have P1 over gamma plus Z1 plus V1 squared over 2G plus H sub S, which is our shaft head, minus H sub L, which is our head loss, is equal to P2 over gamma plus Z2 plus V2 squared over 2G. Now we can do some simplification to this we know, for example, that P1 is equal to P2 is equal to 0. These are all essentially at atmospheric pressure because we're drawing right from the surface of that reservoir, and we're expelling a jet, and so the pressure of both of those will be 0. We also know that V1 is 0 because we're drawing from the reservoir where the surface is at rest, and we're going to define Z1 as 0 as well. That's our datum point. Now we also know that Z2 is going to be 2 meters, and that V2 will be 6 meters per second. And so when we simplify this, we can mark out these terms right here. We know our pressure is 0, and so what we're left with here is we're solving for H sub S is equal to H sub L plus Z2 plus V2 squared over 2G. Now, we were told that our head loss, H sub L, is a function of Q, our flow rate, so 250 times Q squared. So we need to find our flow rate Q. So we know that Q is equal to the area times the velocity, and we're told that the area at 2 is 0.1 meters squared, and the velocity at 2 is 6 meters per second. So we can go ahead and find our value for Q here. And we find that Q is equal to 0.06 cubic meters per second. So that's our required flow rate. Okay, so we can use that to help find H sub L. Now, one thing that we need to note here is that we're looking for H sub S. H sub S includes both contributions from pump 1 and pump 2. So we'll just need to be cognizant of that as we look for our final power required for pump 2. So taking H sub L, our expression for H sub L, this is 250 times Q squared. This is sort of an empirical relationship where you're given the flow rate in a certain unit. So in this case, meters cubed per second, and from this you get the head loss here in meters, so 0.9 meters. And so plugging those values in now to our expression for H sub S, so H sub S is equal to 0.9 meters, which is our head loss at this particular flow rate, plus Z2, which was 2 meters, plus, now we have V2 squared over 2G, so this is 6 meters per second squared over 2 times gravity. And so this gives us shaft work head of 4.73 meters. Okay, so now to find the power required, or the total shaft power required, so W dot S is our shaft power work, or shaft power, so this is equal to gamma times their flow rate Q times H sub S, which we just found. So we know that gamma here is 9.81 times 10 to the 3 newtons per meters cubed. We know that our flow rate is 0.06 cubic meters per second, and our shaft work head here is 4.73 meters. And so when we plug that in, we find a value of 2.78 times 10 to the 3 Newton meters per second, which is, of course, 2.78 kilowatts. So that's the total power required from both pump 1 and pump 2. Now we need to just find the contribution from pump 2. So So we can say that the total is equal to the contributions from pump 1 and pump 2. And we were told in the problem that pump 1 is a 1 kilowatt power pump. And so the total power is 2.78 kilowatts. And so to achieve the needed flow rate and the needed velocity, we require that pump 2 has a power of 1.78 kilowatts.